Welcome to Mech Cosmos. Engineering. Explained. Somewhere in the ocean right now, a ship the size of a city block is moving through the water at 25 kilometers per hour. It weighs 200,000 tons fully loaded. It carries enough cargo to fill thousands of trucks. And deep inside its hull, an engine the size of a 4-story building is turning a propeller 10 meters in diameter, pushing all of that mass through the water continuously, day and night for weeks at a time. The marine diesel engine is the largest and most powerful reciprocating engine ever built by human beings. A single engine can produce over 80,000 kilowatts of power. That is more than 100,000 horsepower from a single machine. It burns fuel so thick and viscous at room temperature that it must be heated to over 130 degrees Celsius before it can even be pumped. It turns at just 80 to 100 revolutions per minute, slower than a ceiling fan. Yet produces torque so enormous it is almost impossible to comprehend, and it runs continuously for months at a time with extraordinary reliability, carrying the goods that sustain the modern global economy. Today we explain everything: how this engine works, how it starts, how it produces such extraordinary power at such low speed, how it drives the propeller, and how the entire propulsion system of a large ship operates. This is the complete engineering explanation of how a ship engine works. We are Mech Cosmos. Engineering. Explained. Let us begin. To understand the ship engine, we first need to understand why it is so different from the engines we have discussed before. The car engine and the jet engine both operate at high speeds. A car engine spins at thousands of revolutions per minute. A jet engine turbine spins at tens of thousands of revolutions per minute. Speed is their defining characteristic. The ship engine is the opposite. It operates at extraordinarily low speed, and there is a very good reason for this. The propeller of a large ship is a massive structure. On the largest container ships, the propeller diameter exceeds 10 meters. The blades are made of nickel aluminum bronze alloy, and each blade alone can weigh over 20 tons. The entire propeller assembly weighs hundreds of tons. To move efficiently through water, a propeller of this size must rotate slowly. If it rotated fast, the tips of the blades would move so quickly through the water that they would create cavitation, the formation of vapor bubbles in the water that collapse violently, causing noise vibration and severe erosion damage to the propeller surface. The optimal rotational speed for a large ship propeller is between 80 and 120 revolutions per minute, and so the engine that drives it must also turn at this speed. But moving a 2,000-ton ship through water at 25 kilometers per hour requires enormous force. Force multiplied by the distance over which it acts is work. Work divided by time is power. To deliver the required power at low rotational speed requires enormous torque. Torque is the rotational equivalent of force. The relationship between power torque and rotational speed means that having the speed while maintaining the same power requires doubling the torque. The marine diesel engine achieves its extraordinary power output at low speed by producing torque values that no other type of engine approaches. The largest marine diesel engines produce peak torques of over 80 million Newton meters. To put that in perspective, a powerful sports car produces perhaps 500 Newton meters of torque. The ship engine produces 16,000 times more torque than that sports car. The type of engine used in virtually all large ocean-going vessels is the 2-stroke slow-speed marine diesel engine. The 2-stroke cycle is fundamentally different from the 4-stroke cycle used in car engines. In a car engine, each cylinder completes a power stroke once every 2 full revolutions of the crankshaft, once every 4 strokes. In a 2-stroke engine, each cylinder completes a power stroke on every single revolution of the crankshaft, once every 2 strokes. This means that for the same engine size and speed, a 2-stroke engine produces twice as many power strokes per minute as a 4-stroke engine. At the low operating speeds of the marine diesel, this is critically important for achieving the required power output. The 2-stroke marine diesel cycle works as follows. The piston begins at the bottom of its stroke. The cylinder is full of fresh scavenging air that has been forced in through ports, openings in the lower cylinder wall, by a turbocharger-driven blower. As the piston moves upward, it first covers and seals the scavenge ports, trapping the air inside the cylinder. The piston continues upward, compressing the trapped air. The compression ratio is high, typically around 14 to 18 to 1. As the piston approaches the top of its stroke, the compression has raised the air temperature to several hundred degrees Celsius. At this point, the fuel injectors fire. Unlike a car engine, there is no spark plug. The fuel ignites spontaneously when it contacts the extremely hot, compressed air. This is compression ignition, the defining principle of the diesel engine. The fuel used in large marine engines is called heavy fuel oil, or HFO. It is the residual product left over after lighter fractions like gasoline and diesel have been refined from crude oil. It is extremely viscous at room temperature, almost solid, and must be heated to around 130 to 150 degrees Celsius to become fluid enough to be pumped and injected. It is also the cheapest and least refined form of liquid fuel available, making it economically attractive for shipping despite its handling challenges. As the fuel ignites, the combustion releases enormous energy. The pressure in the cylinder spikes dramatically, and the piston is driven downward with great force. This is the power stroke. As the piston approaches the bottom of its stroke, it uncovers the scavenge ports again. Fresh pressurized air from the turbocharger blower rushes into the cylinder through the ports. At the same time, exhaust valves in the cylinder head open. The incoming scavenge air sweeps the burnt exhaust gases out of the cylinder through the exhaust valves. This process is called scavenging, and it both removes the exhaust gases and fills the cylinder with fresh air for the next cycle. The exhaust valves close. The piston begins moving upward again. The ports are covered. Compression begins, and the cycle repeats. The pistons in a large marine diesel engine are extraordinary components. The bore, the diameter of the cylinder, on the largest engines exceeds 960 millimeters, nearly 1 meter across. The piston crown, the top surface exposed to combustion, must withstand pressures of over 180 bar and temperatures exceeding 1000 degrees Celsius on every power stroke. The piston is cooled internally by oil circulated through passages inside it. The piston rod connects the piston to the crosshead, a sliding bearing assembly that constrains the rod to move purely vertically. This crosshead arrangement is unique to large marine engines and distinguishes them from smaller diesel engines. It separates the combustion forces from the crankshaft more effectively and allows the very long piston stroke that contributes to the engine's high efficiency. The stroke of the piston, the distance it travels from bottom to top, is very long in a marine diesel engine. On large engines, the stroke can exceed 3.5 meters. This long stroke combined with the large bore gives each cylinder an enormous swept volume. The volume displaced by the piston on each stroke. The swept volume of a single cylinder on the largest marine engines can exceed 1,800 liters. Compare this to a typical car engine cylinder with a swept volume of around 0.5 liters, and the scale difference becomes almost incomprehensible. The crankshaft of a large marine diesel engine is itself an engineering marvel. It is typically fabricated by welding together multiple forged steel sections rather than being machined from a single piece of metal as in smaller engines. The assembled crankshaft of a large engine can be over 20 meters long and weigh hundreds of tons. It runs in enormous plain bearings lubricated with oil under pressure. The main bearings must support the full weight of the crankshaft, plus the enormous forces transmitted by each connecting rod during every power stroke. The crankshaft is carefully balanced, and the firing sequence of the cylinders is designed to minimize the vibration transmitted to the ship structure. The engine block itself is a massive welded steel structure. It is not a casting as in smaller engines. The individual cylinder units are bolted to the bed plate, which is the massive lower structure that contains the main crankshaft bearings. The entire engine assembly is bolted to the ship structure through flexible mounts that isolate engine vibration from the hull. Despite these precautions, the vibration of a running large marine diesel is perceptible throughout the ship. The turbocharger is one of the most important components of the marine diesel engine. It performs two critical functions. First, it compresses the scavenging air before it enters the cylinders. Higher air density means more oxygen per cylinder charge, means more fuel can be burned per stroke, means more power. Second, it recovers energy from the exhaust gases that would otherwise be wasted. The exhaust gases from the engine pass through the turbine side of the turbocharger, spinning the turbine rotor. The turbine drives the compressor side, which compresses the incoming air. The turbocharger is entirely driven by exhaust energy. It requires no mechanical power from the engine itself. Modern marine turbochargers achieve pressure ratios of 4:1 or higher, dramatically increasing the power output and efficiency of the engine compared to a naturally aspirated design. After the turbocharger compresses the air, its temperature rises significantly due to the compression process. Before it enters the cylinders, it passes through an air cooler, a heat exchanger that cools the compressed air using seawater. Cooling the air after compression increases its density further, allowing even more air mass to be packed into each cylinder charge. This intercooling process is a significant contributor to the high efficiency of modern marine diesel engines. The fuel system of the marine diesel engine must handle the challenging properties of heavy fuel oil. The fuel is stored in bunker tanks in the double bottom of the ship. It is transferred to settling tanks where water and solid contaminants can settle out. It then passes through purifiers, centrifugal separators that spin the fuel at high speed to remove remaining water and particles. The cleaned fuel is heated to its operating temperature in heaters and then pumped to the engine at high pressure. The fuel injection system uses individual high-pressure fuel pumps for each cylinder. The pump delivers a precise quantity of fuel to the injector at exactly the right moment in the cycle, at pressures typically between 800 and 1200 bar. The timing and quantity of injection are controlled by the engine management system to optimize combustion efficiency and minimize emissions across all operating conditions. The cooling system of the marine diesel engine uses a two-circuit arrangement. The first circuit uses fresh water to cool the cylinder liners, pistons, cylinder heads, and turbocharger. This fresh water circuit operates at elevated temperature and pressure. The heat absorbed by the fresh water is transferred to a seawater circuit through a central cooler heat exchanger. The seawater circuit uses water drawn from the sea outside the ship, an essentially unlimited heat sink. Using seawater directly to cool engine components would cause severe corrosion and scaling, so the two-circuit arrangement keeps seawater separate from the engine components. The lubrication system circulates oil to all the main and crankpin bearings of the crankshaft, to the crosshead bearings, and to the piston cooling system. Cylinder lubrication is separate. Oil is injected directly onto the cylinder liner walls through small quills to lubricate the piston rings. This cylinder oil must withstand the extreme conditions of direct exposure to combustion gases and must also neutralize the acidic combustion products of the sulfur content in heavy fuel oil. The quantity of cylinder oil injected is carefully controlled. Too little, and the liners and rings wear rapidly too much, and combustion quality deteriorates. Starting a large marine diesel engine requires compressed air. A starting air system stores high-pressure air at around 30 bar in large receivers on the ship. To start the engine, compressed air is admitted to the cylinders in sequence through starting air valves in the cylinder heads. The air pushes the pistons down in the correct firing sequence, rotating the crankshaft and accelerating the engine. Once the engine reaches sufficient speed for self-sustaining combustion, the fuel system is activated, and the engine transitions to running on fuel. The starting air supply is then cut off. The entire starting process takes only a few seconds, but requires a substantial supply of compressed air. The starting air compressors are driven by electric motors, powered by the ship generators, and must always be maintained in operational condition, as the ability to start the main engine is critical for ship safety. The propulsion system connects the engine to the propeller. On most large ships, this is a direct drive arrangement. The propeller shaft is directly coupled to the engine crankshaft with no gearbox between them. This is possible because the engine already operates at the correct speed for the propeller. The propeller shaft runs the length of the ship from the engine room to the stern. It passes through a stern tube, a water-lubricated bearing assembly that seals the hull opening and supports the shaft where it exits the ship into the water. The propeller is fitted to the end of the shaft outside the hull. The propeller itself is usually a controllable pitch propeller on modern vessels. The pitch of the blades, the angle at which they are set, can be adjusted while the engine is running at constant speed. Increasing the pitch increases the thrust. Decreasing the pitch reduces thrust. Reversing the pitch reverses the thrust, allowing the ship to slow down and go astern without reversing the engine rotation direction. This arrangement allows the engine to run at its most efficient speed at all times, while the ship speed and maneuvering are controlled by adjusting propeller pitch. The efficiency of the complete propulsion system, engine, propeller shaft, and all auxiliary systems is a critical factor in the economics of ship operation. Fuel cost is the largest single operating expense for a cargo ship. Modern large, two-stroke marine diesel engines achieve thermal efficiencies of over 50%, meaning more than half of the chemical energy in the fuel is converted to useful mechanical work. This is the highest thermal efficiency of any internal combustion engine in production. The combination of two-stroke cycle high compression ratio, turbocharging, intercooling, and sophisticated fuel injection control all contribute to this remarkable efficiency figure. Ship engines are also subject to increasingly stringent international emissions regulations. The International Maritime Organization has introduced successive tiers of limits on nitrogen oxide emissions from marine diesel engines. Compliance with the most stringent Tier 3 limits in designated emission control areas requires the use of exhaust gas recirculation systems or selective catalytic reduction systems that inject urea into the exhaust to chemically reduce nitrogen oxides. Regulations on sulfur content of marine fuels have also been dramatically tightened, requiring ships to either switch to low-sulfur fuel or to install exhaust gas scrubbers that remove sulfur compounds from the exhaust before it is released to the atmosphere. The maintenance of a large marine diesel engine is an extensive and precisely planned activity. Unlike a car engine that can be stopped at any garage, a ship engine must be maintained while the vessel is at sea by the engineering crew. Planned maintenance schedules specify when each component must be inspected, overhauled, or replaced based on running hours or number of operating cycles. Major overhauls involving removal and inspection of pistons, connecting rods and bearings are carried out at sea by the crew using the engine room crane and workshop facilities. The engine manufacturer provides detailed procedures and torque specifications for every fastener, maintaining the engine in class, meeting the requirements of the classification society that certifies the ship, requires documented records of all maintenance activities and periodic surveys by classification society surveyors. The reliability of modern marine diesel engines is extraordinary. Mean time between failures for major components is measured in tens of thousands of hours. Ships routinely complete voyages of weeks or months without any significant engine issues. This reliability is the product of conservative design margins, careful manufacturing quality control, rigorous maintenance practices, and continuous monitoring of engine parameters to detect developing problems before they cause failures. The ship engine is in many ways the antithesis of the jet engine. Where the jet engine is small, light, and operates at extreme speed and temperature, the ship engine is massive, slow, and built for durability above all else. Where the jet engine is made from exotic single-crystal alloys and precision-machined components, the ship engine is largely fabricated from steel plate and forged components designed to be maintainable at sea with basic tools. Yet both achieve the goal of converting fuel energy into useful thrust with remarkable efficiency and reliability. They represent two completely different engineering philosophies applied to the same fundamental challenge. That is how a ship engine works. We are Mech Cosmos. Engineering. Explained. If this video gave you a new appreciation for the extraordinary machine that drives global trade, then subscribe, hit the notification bell, and join us for the next video. Because every machine has a story, and we are here to tell it.